Hello everyone. What we want to do in this video here is we want to discover a formula for how much money we would have in a bank account after a certain number of time if we were to compound continuously, meaning your money is constantly gaining money throughout the year. Okay, we saw that we could have brute force this type of problem in the last video by using our calculator, using the table on our calculator, but that was really tedious and we kind of had to make a guess at some point. And, well, I don't know, we don't want to have to do that every single time. So let's figure out a formula for it. So before we go ahead and do that, let's do an exercise, a simple exercise that'll kind of lead us to the formula. So here is a simple example. Let's say we invest $1. Let's say we invest $1 at an interest rate of 100%. So we invest $1 at 100% interest rate, on 100% annual interest rate. Okay, and here's the question we're going to ask ourselves. How much money is in the bank account let's say after 1 year, for varying compounding periods. So we want to know what's happening for $1. It's in your bank account. We're earning 100% annual interest. And what we want to know is what is going to happen at the end of that year, how much money will be in that bank account for varying compounding periods. Now, essentially, we're mainly going to ask the question is what happens when the number of compounding periods approaches infinity. So what would this bank account look like? Well, let's think about it. Well, we have $1 in the bank account. We'd have $1 in the bank account. Okay. Well, I'm not going to lose any of our money, so we're still going to have 100% of our money. Okay, our interest rate is 100%. So 100%, I guess, as a decimal would just be a 1. Okay, so I'm taking our 100% interest rate, and we're going to cut this up into n pieces. N pieces. How about instead of n, we'll use m? And you'll see why here in just a second. Let's use m. So instead of n for compounding periods, for this example, I'm going to use m. Just a different letter. So m in this case is the number of compounding periods. Just changing the letter. Okay? And when we would be compounding, in this case, m times per year. Okay, but what we want to know is how much money is going to be in the bank account after 1 year. So we're going to replace t with 1. What happens at the end of 1 year for varying compounding periods? Okay, so I would just have an m up here. Essentially, what we're actually going to ask here is what happens as the number of compounding periods approaches infinity? What if this $1 was in this bank account, earning 100% annual interest, and we're compounding that continuously? So what would happen here as m goes towards infinity? Or what would be happening as m gets extra large, as m gets extra large. Well, let's see. Okay, I'm going to bring us to our calculator. We'll see you there. Okay, let's try to figure out how much money we would have in this bank account as we let m go to infinity. So we're going to plug this into our calculator. Let's do it. We'll go to the y equals. Let's go ahead and erase this. So we had $1. Instead of writing, I guess I could do 1 times, but we'll just put a parenthesis. So we had a 1 plus, maybe I'll have it up here. We have a 1 plus, instead of an m, we'll use an x. So we'll do a 1 divided by, and here's our x. And then we'll close the parenthesis. And we need to raise that. We need to raise this to the power of m, or in this case, x. That's what we're using in replacement of m. Okay, so let's see what happens here. Okay, so then we'll go to our table set. Okay, let's let's go ahead and start out at 0, and let's move up in increments. Let's not go too fast, too quick. Let's move up in increments of, I don't know, how about 100? Let's see what happens. Okay, so let's go back to our table. I'm gonna just get in a better grip. Oh, our table, and let's see what happens. Okay, so let's go down. Let's see how much money is our dollar growing to? If we try compounding this would be continuously. We want what's happening for extra large M, or in this case, extra large X. Okay, so we could keep going. It looks like it's kind of evening out on this number here. Can we get it any higher? Let's go. Let's get a little bit better accuracy. Let's see, do the best we can. Let's be crazy. Let's move up in increments of, I don't know, 10, 100,000. Why not? Let's see what this does. Okay, let's go back to our table. Okay, let's scroll down. So it looks like, it's showing us 4 decimal places, but I mean, we're going out pretty far here. Notice it's using scientific notation here. This e to the, get a better grip. This E6 means 1. I mean, this is 4.01 times 10 to the 6. That E means times 10 to the 6. So it looks like our $1 our $1 earning 100% annual interest. If we were to compound that continuously at the end of 1 year, it looks like we'd roughly have roughly 72 cents. So let's go return back to the video and talk about this. Okay, we just discovered that our $1 invested at 100% annual interest rate at the end of 1 year, how much money we would have if we let the number of compounding periods go to infinity. Essentially, we're thinking about this $1 at 100% annual interest rate being compounded continuously. Looks like we roughly got, was it 2.7183? So if we take this expression here and we let m go to infinity, if we let m get extra large, if we let m get extra large, then we get this very special number. We call this number E. E. This is a very special number, E. E. E is an irrational number, and it's roughly 2.7183. This is roughly what this number is equal to. This is an irrational number. This is irrational like pi. Irrational number like pi. Pi is an irrational number. Just means that it's decimal version. The decimal version, it's decimal. It continues on forever, and the numbers don't have any sort of pattern to them. So E is an irrational number. It's called Euler's number. Euler's number, after the mathematician Euler. Euler is spelt with an E. Euler's number. Euler's number. It's one of the most important numbers in mathematics. We've derived it here in terms of compound interest. However, it has lots of other applications, and it pops up all over the place, specifically in calculus. E is the best number in calculus. They sometimes say, E makes calculus easy. They say that, I don't say that. They say that, I don't say that. So, this is the number E, a beautiful number. It's in your calculator. It's in your calculator. So notice here in your calculator, well, if you look here, right above the caret, you see that there's the famous pi number. But right below, the division sign, above the division sign in blue right there, there's the famous number E. We can get to it by first pushing the second button, and then pushing the division sign. So we have that number E, and if we hit enter, we're getting its decimal approximation, 2.71828, 2.7183 if we're rounding to 4 decimal places. But there's our famous number E. There it is. So we're going to need this here in just a second. We discovered one of the most important numbers in mathematics. We're going to take this and we're going to hold it over here. It's going to be a great tool. What we've just discovered is that the limit as m goes to infinity. I just want to know what's happening to the expression as m gets really large of a 1 plus 1 over m to the power of m. We just discovered that this is the famous number e. Here's one definition for this number e. Okay, let's hold on to this. This is going to be helpful. So here we are, happy that we discovered such a beautiful number. And we're going to hold on to this. We're going to hold on to it. Okay, so let's now derive the formula for compound interest. So what are we going to do? We're going to first take the formula for discretely compounding. So what do we do when we compound discretely? Well, what do? We have the principal, the amount of money we put in our bank account. Okay, we have 100% of our money. We're not losing our money, but we're gaining. Okay, well, what are we gaining? Well, we have our interest rate, but we're taking our interest rate and we're cutting it up into n pieces. Here I'm going to use n now. So we're cutting up into n pieces, and we would be compounding n times per year. Okay. So if we want a formula for compounding continuously, what we want to do is we want to know what happens to this expression as the number of compounding periods approaches infinity. We want to know what is the limit. What is the limit as n goes to infinity? This will be a formula for continuously compounding as a function of time. Continuously compounding as a function of time. Okay, well, let's play around with this. I'm trying to figure out, can I somehow write this expression without this ugly limit? This is just basically saying, hey, plug this thing in your calculator and use your table function and let that n get really large and see what's happening to the output. Okay, but I wish I could somehow kind of like fit this piece in here somehow. And let's figure out how we're going to do this. Okay, let's figure out how we're going to do this. Well, it'd be really nice if there was a 1 over m here. It'd be really nice if there's a 1 over m here. Okay, well, let's just say, for example, let's let m, so we're just going to define a new number. We're going to call it m. We're going to call it m. Let's let m be the same thing as, let's say you take the number of compounding periods and you divide it by your interest rate. So if you know how many times you're compounding, you know your interest rate, you divide the two. That's what I'm calling m here. Okay, why did I define m this way? Well, notice if I reciprocate everything. If I reciprocate everything, since, if you think of this as over 1, and I reciprocate both sides, that means that 1 over m would be the same thing as n over r. It would be, r over n. R over n. I'm reciprocating both sides. R over n. So it'd be nice that we can make a replacement right here. So that's how I'm defining m. Okay. Also, another thing to note here, so I reciprocated both sides, so we got this out of, we defined m to be n over r, so that means 1 over m would be r over n. But also, if we multiply both sides by r, we also have that n would be equal to the same thing as m times r. So maybe this will help us, I don't know. We're making a replacement. Okay, so let's plug that in up here. So we have our principal, and now we have a 1 plus. Okay, well, let's see here. Well, r over n is the same thing as 1 over m. 1 over m, cool. And our n here is the same thing as m times r. So I'm going to replace n with m times r. So m times r times t. So this n is being replaced with m times r. Okay, so we're still going to have this limit, but let's think about what's happening here. So notice I have no more n's here, I only have m's, and so I don't want to take the limit as n goes to infinity. Well, let's think what would happen. Okay, well, let's think about r being fixed here, for example. So maybe r is 0.08. But think about here, as n is getting really large, as n is getting really large, m is also getting really large. M is also getting really large. So, what do we want to do? If I'm taking the limit as n goes to infinity and I'm replacing with this m's, this would be the same thing as me saying, now as m goes to infinity. These here are equivalent. Kind of just done a variable replacement. Okay, well, let's play around with this a little bit more. So we're taking the limit as m goes to infinity. Okay, I'm going to clean this up a little bit. I would like to see a 1 plus 1 over m to the power of m. Well, there's that nice exponent rule. There's that nice exponent rule that if you have, like, I don't know, like an x to the n to the m, then this is the same thing as x to the n times. And maybe I should use different letters. I mean, these n's and m's are different. So I don't know. Let's say we have x to the L to the K. Well, this is the same thing as x to the L times K. So oftentimes you're probably used to using this exponent rule this way, but we're going to use it this way. So if I kind of separate these two pieces here, this would be equivalent to put a bigger parenthesis here. Well, this is the same thing as 1 plus 1 over m, okay? And then the m is going to hit here, and I still have my RT on the outside. So I have our RT. So I just put this m on this set right here. Notice this rule said that these would multiply and it'd be right back here. Okay, well, notice that this is very fruitful. So if I'm taking the limit as m goes to infinity of this expression, well, as m goes to infinity, 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 what is this doing? What is this doing? That's E! That's E! E! It's E! It's E! So what do we have here? What do we have here? This is still continuously compounding as a function of time. Continuously compounding as a function of time. Well, now we are continuously compounding as a function of time. Now it's just P, but this is just E. E. And then to the RT, or we get P times E to the RT. And there we have it. Here we have it. The formula for continuously compounding. The formula for continuously compounding. Let's write this up. Let's write this up. Okay. For continuously compounding. Continuously compounding. For continuously compounding, the formula C of t is equal to P times E to the RT. Or the way I remember this is PERT. It says PERT. PERT. That's how I remember it. This is the formula for continuously compounding. Let's test it. Let's test it out. Let's test it out. What did we have in our last example? In the last video when we brute force something like this? Grandma, what did they do? Grandma put, what was it? It was $12,000 or $1,280 in our bank account. Okay, well, what were we doing? Well, our interest rate, I think, was 8%. It was 8%, and we wanted to know what happened after 18 years. After 18 years. Okay, well, let me just check our notes. What did we figure out? In the last video, I'm going to say, last video, we brute forced it with a table, and Grandma hooked us up with $5,402.50. Ballin'. That's what Grandma hooked us up with. Okay, well, can we get that same answer using this formula rather than the table? I hope so. I hope so. Okay, well, if I'm plugging all the pieces in, our principal was $1,280. Okay, then we have E. We have E to the R times T. So this would be 0.08 T. So this is now would tell us how much money we'd have in our bank account, or how much money Grandma put into our bank account, how much money we have at the end of T years if we're compounding continuously. But what about 18? What happens after 18 years? E to the 0.08 times 18. Let's plug this into our calculator. Okay, you could use this E button above the division sign, but also notice right above this says ln, which stands for natural logarithm. We'll talk about that more in a second. We see something that says E. What to say? E to the power of x. E to the power of x. So when I'm typing this in, I'll show you in just a second. We'll do 12, 1, 2, 8, 0, and then we'll hit, since it's blue, we'll hit the second, and then we'll do the E. It's going to do, now E to the power, it's already going to open up a parenthesis, and we'll do 0.08 times 18, close that parenthesis. This is what I've typed in. This is what I've typed in. Let's go ahead and enter. Drum roll, please. Drum roll, please. Drum roll, please. Oh my goodness. Oh, look at that. And look at that. They're the same. It works. It works. It works. We didn't have to use a table. Oh, isn't math great? Isn't math great? Okay, this says, you know, 49, your calculator was rounding. It was rounding when we did the table. But it's the same. It's the same. It works. This is great. This is great. So this is the formula for compounding continuously. Okay, so we have two formulas for compound interest. One where we compound discretely and one where we compound continuously. If we're compounding discretely, that means a fixed number of n. That means we're cutting up our year into n pieces. So we'd have our principal, we'd have the amount of money we put into our bank account. We're not losing our money, we're still going to have 100% of our money, but we're gaining. Well, how much are we gaining? Well, we're going to take our interest rate, we're going to cut that into n pieces, and then we'd be compounding n times per year. So this is the formula for compounding discretely. If we're compounding continuously, what we did is we took our year and we cut it up into an infinite number of pieces, so we would be continuously getting interest throughout the year. And how we got that formula is we took this formula and we thought, what would happen as n got really, really, really large? Essentially, what happens as the number of compounding periods approaches infinity? And we figured out the formula was equal to P times E to the RT, or I remember this just the word PERT. Okay, so notice again that there's no n in this formula. There's no n in this formula. Why? Remember how we derived this formula? We took this formula, we let n go to infinity. So there should be no n in the continuously compounding formula. Let's do an example. Let's say you invest. Let's say you invest. Let's say, I don't know, how about $5,000? $5,000 in a bank account earning, I don't know, let's say 6%. 6% annual interest. 6% annual interest. Okay, question. So we'll have a two-part question. Question one, I want to know how much in your bank account, or let's do it right here. How much in the bank account let's do, how about after 10 years if, okay, so question one, how about compounding, let's say compounding, how about semi-annually? Okay. How about question two? How about continuously? Or how about question two? Yeah, let's just do continuously. Continuously. Okay, go ahead and pause the video and try to do this on your own. Okay. Let's do it. If we're compounding semi-annually means I'm compounding twice per year. Okay, so how much money we would have at the end of 10 years? Well, what will be our formula? We'd have our M of T. Well, the principal is 5,000. Okay, we still have 100% of our money. And what are we doing? We're taking our 6%. We're taking our 6% annual interest rate and we're cutting it into two pieces. And we would be compounding twice per year. Okay, so we would want to evaluate this function, how long we're waiting, after 10 years. Okay, so let's use our calculator. So you'll just replace t with 10. So let's see what we have. So 5,000, 1 plus 0.06 divided by 2 to the power of parenthesis 2 times 10. And it looks like I'm getting I'm getting $9,030.56. Pretty good. It's pretty good. Okay. What if we were compounding? What if we were compounding continuously? So continuously. Well, we would have that our function c of t. Okay, compounding continuously. We have the $5,000 in our bank account. Now we're going to multiply by e. Okay, our interest rate is 6%, 0.06, and we're going to multiply that by t. So now we'll just want to evaluate this at 10. Okay, so we'll have 5,000 times. Okay, we'll want to use the e to the x button, above the natural log button, the ln button. So second ln. So e to the 0.06 times 10, close the parenthesis, and here we're getting $9,110.59. Not a surprise that it's more in this case because I'm compounding more often. Okay, so let's go ahead and now do an exercise where we're going to be talking about something that's called APY, or the annual percentage yield. The APY, annual percentage yield. The APY is something that bank accounts or banks have to report to you. They have to report it to you. So let's talk about what APY is. The APY is a way to compare bank accounts, possibly with different interest rates and different compounding periods. So let's talk about the annual percentage yield. The annual percentage yield. Okay, this is sometimes called the APY, and this is often something a bank will report to you. They'll tell you your annual percentage yield, which just means an annual interest rate. So what is this? It's just kind of a few notes here. This is a way to compare bank accounts. Okay, and what is it? What is it? Make a few notes here. So what is it? It's the interest rate. So the APY is the interest rate that yields the same amount if compounded annually. So that's what it is. So let me just kind of do an example about how to think about this. There's a formula for this, but I mean, for whatever reason, I just prefer just to think my way through it. So for an example, let's compare a couple of different bank accounts, and we're going to decide which one's the best. So there's Bank A. Let's move this over here. So there's Bank A, and we'll call it, and there's Bank B, and there'll be Bank C. So Bank A, let's say you have an 8.2. This is an 8.2 annual interest rate, and we're going to compound annually. So this is going to be, this is interest rate. That's what I'm going to put here, and this is compounding period. Compounding period. Okay, so for this bank account, it's annually. Okay, for Bank B, let's say it's 8%. So we have a lower interest rate, but let's say it's going to be compounded monthly. This is compounded monthly. Okay, Bank C here. Let's say this has a lower interest rate. Let's say this is a 7.9% interest rate, and let's say it's compounded continuously. compounded continuously. I want to know which bank account is the best. Which bank account should you choose here? Different interest rates, different compounding periods. And the way we do this is we want to figure out what would be an equivalent interest rate. And for the example here, we're compounding 8%. So we have an interest rate of 8%. We're compounding monthly. Well, what would be the equivalent interest rate if we were actually compounding just once per year rather than 12 times per year? And that's what the APY is. Okay, so for this one right here, since we're already compounding annually, let's kind of write this up. So I don't know, you'd put a certain number into your bank account, the principal. Okay, and what would you set up here? Well, you'd have 100% of your money and you'd be adding 0.082. So this is the interest rate, but you'd only be cutting this into one piece and you would be compounding once per year or just T. So since here, the APY is the interest rate that yields the same amount if compounded annually, since this bank account is already reporting you the interest rate when we're compounding annually, here the APY and the interest rate are the same. So here, let's rewrite this. Let's write this as P. We're going to write this as 1 plus a, how about we write it as 1.082 to the T. So the APY here, in this specific case, the annual percentage yield is the same as the interest rate because we're already compounding annually. The APY would still be 0.082 or 8.2%. Okay, what would be the APY for this bank account? Well, let's think about it. So I would still put a certain amount of money in my bank account, the principal. Okay, we would do 1 plus, we would take our 8%, 0.08, okay, and we would cut that into 12 pieces, and we would compound 12 times per year. What I would like to do is I would like to massage this formula so it looks to my eyes that we would be compounding only once per year rather than 12 times per year. So I could just do a little massaging here, use a little bit of our exponent rules. This is equivalent to me writing a 1 plus 0.08 over 12 to the power of 12, all raised to the power of t. I'm using the exponent rule that x to the n to the m is equal to the x to the n times m, except I'm actually doing it in this direction. I'm doing it in this direction. Okay? So now I'm just going to compute what's on the inside right here. So what we have here is we have 1 plus 0.08 divided by 12 to the power of 12. So I'm just computing this piece right here and I'm hitting enter. And this is saying we'd have the principal times, in these parentheses, times, we'd have a 1.0808, let's say 2999. We'll kind of go out to the power of t. To the power of t. So in this case here, we could say that this is roughly, let's just round it up. So 1.083 roughly. 3. So notice here that this smells or this looks a lot like I was just compounding once. It looks like I'm just compounding once per year rather than 12 times. So I can almost read what this interest rate would be here. This would be like, 1 plus 0.83. So essentially I'm taking this number in the parentheses and I'm subtracting 1. So here the APY would be 8.3% or 0.083. What this is saying is that if we compound at 8% monthly, this is equivalent to compounding at 8.3% annually. So this is the APY. It's an equivalent interest rate if we are compounding annually rather than compounding monthly. Okay. So right off the bat, which bank account would you choose? Well, this has a better APY, so this bank account is better than this bank account. How about continuously? Well, what would we have here? Well, we have the money that's in our bank account, our principal, and it would be E. Okay, our interest rate is 7.9%, so 0.079 times t. This is if we were, compounding continuously. But I want this visually to look like I was compounding annually. So we'll just do some massaging. We'll do some massaging. So how about we write this as e to the 0.079 all to the power of t. So let's figure out what e to the 0.079 is. So e to the 0.079, I'm getting that this is a p. We're going to get a 1.0822 to the power of t. This now visually looks like I'm compounding once per year rather than continuously. So, these look a lot the same. These look the same, except over here what our APY would be, over here our APY would be 0.0822. So, compounding at 7.9% continuously is equivalent to compounding with an interest rate of 8.22% annually. So, which bank account is the best? Well, B is the best. It has the greatest. Well, let me move the screen down. B is the best. It's got the best annual percentage yield. This is a way to compare these bank accounts. So, your bank legally has to tell you the APY. It has to tell you the APY. They don't want banks confusing people. They're saying, "Oh yeah, sure that bank is giving you 8% monthly. Well, we'll just give you 7.9%, but we'll compound continuously. Doesn't that sound great? Doesn't it sound great?" Maybe you're sitting there like, "Oh, I don't know. I don't know what's better. I wish I had a way to compare these bank accounts. Can you tell me like some sort of equivalent interest rate? If you were like, maybe let's just pretend like we were just compounding once per year. What would be the equivalent interest rate?" That's the APY. The equivalent interest rate, if we're compounding once per year, that's the APY. Looking at all these, ding, 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 you'd want to pick Bank B. You'd want to pick Bank B. So that is the APY. Okay, let's have you try one of these type of problems. Let's have you try one of these type of problems. Okay, let's compare some bank accounts. Okay, so which account would you choose? Which account should you choose? Which account should you choose? Well, let's say you have an annual interest rate of 5.125%, and let's say it's compounded semi-annually. And let's say, how about 5% compounded continuously? Okay, I want you to do this by finding the APY and then you telling me which bank account is better. Give it a shot. Okay, let's do it. So for this first bank account, let's set up what the formula would look like. You don't have to put a P here, but you could pretend, putting some sort of amount of money in my bank account. Okay, we got 100% of our money. We have an interest rate of 0.05125. Let's cut that into two pieces, and we'd be compounding twice per year. Okay? So let's see this as being the same thing as a 1 plus 0.05125. Cut that in half, just raise it to the power of 2. So now this is going to look like we're just compounding once per year. So let's figure out what this number is. So we have a 1 plus a 0.05125 divided by 2 to the power of 2. So I have a P. We have a 1.05 Let's go 5. Let's go 1, 9. So it's not exact. It looks like I'm going out to 4 decimal places to the power of t. So now what I have is this formula that looks like we're compounding semi-annually. I've kind of just massaged the formula to make it look like we're now compounding just once per year. If we're compounding once per year, what would be the interest rate? You'll just take whatever this number is in the parenthesis and you'll subtract 1. So here, the APY is going to be 0.0519. So I could compound semi-annually with an interest rate of 5.125%, but this would be equivalent to us compounding annually at 5.19%. Okay, well, what if we're doing this one where it's continuously? Okay, well, we would have P, and we would get E, so it's PERT, remember the PERT. Okay, so it would be 5%, so 0.05 times T. Okay, this is if we were compounding continuously, but let's try to make it visually look like we're just compounding once per year. So e to the 0.05 to the power of t. So we just need to figure out what e to the 0.5 is. So e to the 0.05. So this would be p. And now we're going to get I have a 1.05127 roughly to the power of t. So, or if we're going, I guess I went out to 4 decimal places here. Let's go out to 4 decimal places here, so I'd round this up to 3. So here, we would have an APY, okay, so just take this number in the parentheses and subtract 1. We would get a 0.0513, or a 5.13%. Well, which bank account is better? Well, the bank account that has the annual percentage yield, or an APY, of 5.19, this one's going to be better. You're going to want to choose bank, the one that compounds semi-annually. Okay, we have a higher interest rate. We're compounding semi-annually. You might be confused at the bank if the bank tells us, oh, you have these 2 accounts. This one is 5.125% semi-annually or 5% continuously. You may be like, I don't know which one to choose. Well, the bank legally has to tell you the APY. So they'd have to say is, well, this bank account would earn you 5.19% compounded annually. This bank account will earn you 5.13% compounded annually. So now you can compare the two and see that bank B, or this bank here compounded semi-annually, is your best choice. I hope you enjoyed these videos on compound interest. I hope you enjoyed learning about E. Here we've talked about E in terms of compound interest, but E is one of the most beautiful numbers in math. It's going to pop up all over the place in calculus, all over for those who are going further math. E pops up everywhere. So in the next video, what are we going to start doing? We're going to start thinking about the inverses of exponential functions. We'll see you there. Take care.